everyone. In this video, we will learn chapter 23. This is about entropy and gives free energy. This is our learning outcomes. You should be able to explain about entropy, the difference in magnitude of entropy for change state, change in temperature, for a reaction which there is change in the number of gas molecules, predict whether it is positive or negative, calculate the delta as standard, and then in the next video, we will learn about the Gibbs free energy and about spontaneity. If a bottle of a carbonated drink is left open, we expect it to the test would be fine flat after a couple of days. Why? Because the carbon dioxide escapes from the solution and diffuses or spreads out into the wider surrounding. We do not expect all the carbon dioxide to return at a later date. This would not return, right? In a similar way, a hot cup of coffee will cool and lose some heat to the surroundings. The heat will not return. Both these examples illustrate a general principle that energy and matter tend to disperse, and the surrounding, the universe, becomes more disordered. These are both examples of spontaneous change. They occur naturally without the need to do work. Actually, we carry first the natural tendency of change, but only at the expenses of doing work. So let's say if you want to make the heat back to this coffee, you should boil it up again, right? You need to do work. So this is a not spontaneous reaction. But when you leave it cool, it is spontaneous. Similarly, sodium and chlorine have natural tendency to react together to form sodium chloride. We can reverse the process and split the sodium chloride into its constituents, but only if you give the energy, if you give the electricity using the redox reaction, the electrolysis, and it needs to do work. Yeah, you need to do work. So this is spontaneous. This is not spontaneous. Bubble rise and escape from a carbonated drink. This illustrates a general principle. Once again, matter and energy tend to disperse and becomes more disordered. Such everyday experiences can be expressed more precisely when the degree of disorder of a system is quantified by its entropy. The symbol is capital S. Entropy refers to the distribution of available energy among the particles. The more ways the energy can be distributed, the higher the entropy. Order state with a small energy distribution are said to have low entropy. Disorder states, called as high entropy. This is high energy distribution, high entropy. As time moves forward, matter and energy becomes more disordered, and the total entropy of the universe will be increases. Okay, this is actually this picture shows us about the second law of thermodynamics, which is one of the most important law in science. So what is entropy? Entropy is a measure of the dispersal of energy at a specific temperature. It can also be thought as a measure of the randomness or a disorder of a system. The higher randomness, the greater the entropy of the system. This is ordered, low entropy. This is disordered, high entropy. So which has the highest entropy? Yes, the right one. Okay. Disordered, high entropy. When a piece of potassium manganate was placed at the bottom of the beaker at 12 o'clock, 2 hours later, it has diffused. It has diffused throughout the water. Through the reaction, KMnO4 solid becomes K plus AQ with MnO4 minus AQ. These aqueous ions have higher entropy than the solid crystal. Entropy increases with time. Now text looks about diffusion and number of ways. We can show that there are 3 molecules in the gas jar A, separate with the gas jar B by the partition. In this model, we assume that there are only a few molecules in gas jar A, no particles present, and the molecules move randomly and change directions when they collide. After we remove the partition, what happens? The molecules can move randomly not only in the gas jar A, but also into the gas jar B. Okay, there are 3 molecules and 2 places in which they can be. So the number of ways of arranging of the molecules after removing the partition is shown here in this figure. There are 8 possible arrangements. It can 1, 2, 3 at the gas jar B. It can 2 and then 3, 1 in the gas jar B, etc. So if once again there are 2 gas jars and there are 3 molecules, so the formula to find the number of possibility of arranging of these 3 molecules is 2 to the power of 3. 2 because of the 2 gas jars and then 3 because of the number of molecules. So there will be 8 possibilities of arranging. Okay. Now, take a look in the change in state process. We can see that this is solid, low entropy, change to liquid, and then to the gas. If we increase the temperature, we increase the entropy. Since highly disordered, the gas has high entropy because highly disordered. Okay, now let's see about the graph between entropy versus the temperature in the changing states of matter. Yeah, you can see that if the solid increase in the temperature, then it will reach its melting point. Okay, so when we gives heat, the entropy of the solid will be increases. Also, the temperature will be increases. The temperature increases, entropy will be increases as well. But in a melting point condition, the temperature will be stay, but the entropy will still increase. After it reaches the melting point, Then the temperature will rise again, also the entropy. And then after it reaches its boiling point, when the liquid changes to gas, the temperature will be stay again, yeah, to change the state, but the entropy will be increases, still increases until it reaches the gaseous state. Then the temperature will rise again, and also the entropy. So when a substance has a zero entropy, when this condition occurs at absolute zero or negative 273 degrees Celsius. This is 0 Kelvin. At these conditions, a crystal has a perfect order, so zero entropy. This is called as the third law of thermodynamics. So as conclusions, the temperature increases, disorder increases, and entropy increases. This is the summary. If we change the solid to liquid, the entropy will be increased. Solid gas, liquid gas increase, liquid solid decrease, gas solid, gas liquid decrease. Okay, now let's practice. For this question, refer back to the figure 23. This is this. If there are 4 molecules in the gas jar on the left, how many ways of arranging of the molecules are there when the partition is removed? What's your answer? There will be 2, because there are 2 gas jars to the power of 4. This is 16. Okay, so there are 16 ways of arranging the molecules when the partition is removed. What is the probability of finding all 4 molecules in the right hand gas jar? What's your answer? There are 16 ways. So probability of any one of these arrangements is 1 in 16. Yeah. Okay, now let's see question C. Which of the following changes are likely to be spontaneous? Okay, I'd like you to answer this first. Please pause the video. Okay, let's check your answer. Sugar dissolving in water? Spontaneous. Diffusion, right? The smell from an open bottle of HS ammonia diffusing throughout the room? Spontaneous. Water turning to ice? Not spontaneous. You need to keep it in a refrigerator, right? Ethanol vaporizing at 20? Spontaneous. Water mixing completely with cooking oil? Not spontaneous. Limestone decomposing at room temperature? Not spontaneous. You know, this is a thermal decomposition. You need to give heat for the decomposition reactions to occur. So not spontaneous. Okay. Now let's see another practice question. Once again, pause the video. Okay, let's check your answer. Predict the entropy change for the following changes. Br2 liquid to Br2 gas. So the entropy change will be positive. Cu solid, O2 gas, CuO solid. So this is negative because gas disappear to form the solid. C negative because aqueous change to solid. D delta S will be 0 since there are two gas molecules at the left side and two molecules of gas molecules at the right side, 2 and 2, so entropy will not change. E negative. Why? Because there are two gas molecules at the left but only one at the right, so more ordered. Yeah, so negative. F delta S will be equals as 0 since aqueous solid, solid aqueous, so balanced, right? So there will be no change, so the entropy change is 0. Okay,